Hello, I am Saurabh Bansal. I am a co-founder of CompilerAI Labs, which is a startup that has spun off from our research group at IIT Delhi. Compilers are under increasing pressure because of improvements or advancements in programming languages and increasingly complex ISAs necessitated by the end of Moore's law. And this can be seen in the growth of compiler complexity. This chart shows the number of lines of code in thousands in GCC compiler from 1992 to 2021. While the number of lines of code in 1992 was less than 100,000, today the number of lines of code in GCC stands at over 18 million. This drop in the line of code at around 2016-17 is because of deprecation of a certain garbage collector. But in general, the trend has been of increasing number of lines of code, also indicating increasing complexity. This is not just specific to a particular compiler. If I look at LLVM, and in this case I'm plotting the number of lines of code in the optimization and code generation logic of LLVM over time, starting from 2001. And once again, we have over 3 million lines of code just in the optimization and code generation logic of LLVM. Has been increasing gradually. And this is not showing any signs of slowing down, and I would imagine that this will keep going on, going further in future years, if not at a faster pace. The symptoms are visible when you kind of look at the number of bugs that are found in compilers, in modern compilers. So you can go to the GCC Bugzilla page and search for bugs. For example, you can use this keyword called wrong code. I did this experiment a few days ago, and I found that there were 15 wrong codes being either reported or being discussed or assigned in the month of July 2022 alone. And you will notice that these bugs are pertaining to different kinds of optimization levels like O2, O3, OS, etc. And so basically a lot of these bugs, or most of these bugs, are in the optimization logic of the compiler. A similar study on LLVM can be done. You can go to the LLVM's GitHub page and use this keyword for searching is:issue label miscompilation. Miscompilation bugs are kind of wrong code bugs where the compiler silently generates wrong code, and these are the most dangerous type of bugs because they give no feedback to the programmer. And once again, basically there are 98 open, 409 closed bugs since 26 November 2021, which is the date when LLVM migrated to GitHub. Now, as a result of all this, one of the big issues with general source code is unintended undefined behavior in programs. So many programmers, or most programmers I would say, are kind of not fully aware of all the subtleties of C semantics, and so they often write code that kind of executes fine when you use a certain compiler with a certain optimization option, but as soon as you change the compiler basically leverages the code to do more aggressive optimization and your code starts failing. Here's an example. So let's say you have a variable A which has two shorts, and you basically assign these constants to these two shorts, 1, 1, 1, 1. And then and the programmer basically decided to typecast A as an integer, as a pointer to an int, and then assign 2, 2, 2, 2 to this value, and then print both these values. Now, the programmer was probably hoping that he'll get 2, 2, 2, 2 as the answer when it prints it. And if you don't use optimizations, then indeed that's what's going to get printed. But if you turn on optimization, certain compilers will often reorder such writes, because as per C semantics, this program has undefined behavior, and it may print any random value or may just exit or do any random thing as well. Now these kind of bugs kind of lurk in source code, and just because the compiler is not exploiting these issues for optimization, they kind of remain in the bug. But as soon as you change the compiler, these bugs kind of show up, and this is one of the reasons that people are very scared to change compiler versions or compilers. Here's another example related to floating point precision. So let's say you have a variable x, you give it some value, some floating point value 0.012, this is of type double, and then you add 1.0 to it. Now you do the same. Let's say there's another function test, and in this test function you do the same thing. You use do x plus 1.0, but this time you assign it in a different variable y. Now let's assume that these functions test and main are in different compilation units or different files, and so what can happen is that for the first program, the value of y computed can be different for the value of y computed by the second, so the value of y and y2 can be different, because in this value of computation of y, the compiler can do constant propagation, assuming that the double is a certain bit width, say 64 bits, which is the general case. And in the second case, when you compile it for a 32-bit x86 architecture, the machine may use the floating point stack on the x86, which is of a different bit width, so 80 bits. So when you do the same plus operation in a different bit width, which is 80 bits, versus if you do it in 64 bits, you get different answers. And so what happens is that for certain compilers and certain optimization options, you get error implementations. That means error gets printed, whereas for some other compilers and optimizations, you don't get error. Now these are subtle errors that programmers are often not aware of, but these are important issues because these can cause all kinds of numerical instabilities. And in fact, we have a well-documented case where there was a rocket explosion because of floating point precision and double rounding errors. Now, if I look at the compiler ecosystem, it's increasingly interdependent, where multiple organizations are kind of contributing to the same code base and kind of also using the same code base. And that makes it even harder to ensure that the compiler is trustworthy, especially when it comes to critical software systems such as those found in aerospace, defense, transportation, and energy. Now, many of these critical sectors are governed by software standards such as the DO-178C standard for aerospace. The DO-178C standard basically requires that the object code is validated, that it is doing what it's supposed to do. Now, this is a very difficult problem because checking assembly code is manually very difficult, and also static analysis tools are not very precise at being able to identify what's going on at the assembly level. So in practice, compliance is based on ad hoc methods. For example, they would compile small programs and manually verify that the assembly is correct for small programs, and based on that, they will extrapolate and say that the compiler is correct. Or they would use some kind of structural code coverage metrics to ensure that to kind of reach some level of satisfaction that the code generated by the compiler matches with the source code. But all these problems, all these kind of methods are ad hoc and quite unsatisfactory. Moreover, critical software development teams like those found in aerospace and defense often just disable or compiler optimizations to kind of avoid or sidestep these problems. And as a result, they take a performance hit of up 2 to 10x, and this is especially critical in these environments where the computers are often, special computers hardened for high pressure, high temperature, and also legacy systems where these performance hit basically often leads to feature disabling to fit within resource constraints. Moreover, unintended undefined behavior is rampant in source code, and that basically forces organizations to use 10 to 20-year-old compiler versions because they know that an aggressive optimization pipeline may expose the bugs in their source code. Our solution is a formal equivalence checker between the source code and the object code across an optimizing compiler. Using this equivalence checker, you can get strong guarantees on the correctness of the compilation. This work is based on over 10 years of high-impact research in this space done at IIT Delhi. So our product, which we call a translation validator, and it's also known by that name in the research literature as well, basically works as follows. So let's say you have some higher language source code. We support the C language. You use an untrusted optimizing compiler to generate some machine code. Let's say we support x86, and then we give these two programs, the C source code program and the x86 machine code program, to a translation validator. The translation validator then tries to identify an equivalence proof between the two programs, and if it is able to identify a proof, we say that the executable is certified against errors. In other words, the x86 machine code emulates the C language source code. If there's a separate analysis or separate code analysis for the source code, which basically certifies the source code against certain errors, then together with this equivalence proof, we are sure that the executable is also certified against errors. This can be also seen in this picture where the source code is run through an untrusted compiler optimization pipeline to obtain the machine code, and you use our equivalence checker or translation validator to check that the source code and machine code are they equivalent or not. And our equivalence checker has certain properties which are very important. First of all, it's end-to-end, which means it makes no assumption of what the compiler is doing within. It tries to find a proof without knowing the exact transformations that the compiler has done. It supports loops, aliasing informations, and all the general programming constructs like function calls, etc., that people typically use in imperative languages. Importantly, it has no false positives, which means if the equivalence checker generates a proof, it's a guarantee that it's a formal guarantee, in terms of formal verification or formal methods, that the source code and the machine code will produce identical outputs for all possible inputs when executed. And it minimizes false negatives, which means if the equivalence checker says that I could not find a proof of equivalence, it does not necessarily mean that the two programs are inequivalent. Such a situation would mean that it's a false negative. Our tool attempts to minimize false negatives, and that has been the subject of our research, and that's been the primary result based on which we are building the tool, that the tool has very few, if any, false negatives, and especially when the optimization levels are within bounds, for example. All right, so I'm going to proceed to my demo to show this in action. So we have built a Visual Studio VS Code extension, and we can use this to basically check equivalence. So in my first example, I'm going to show equivalence of two C programs. My first program is strlen_source, and the second program is strlen_dest. So it's two different function implementations of the strlen function in the C library. So the source program can be seen on the left, the optimized implementation can be seen on the right, and in the middle, the equivalence checker has kicked off and it started running and trying to compute an equivalence proof between the two. While it's running, let me walk you through the two programs. On your left, you see a strlen program, which basically takes a pointer to an array of characters and identifies the location of the first null character. When it finds a null character, it breaks out and it basically gives the distance between the null character's location and the start location S. That's return P minus S. While this is a very easy implementation and easy to understand, the actual implementation that actually exists in optimized C libraries looks something like that on the right. In the right, basically the first thing the implementation does is it aligns the PTR to a 4-byte or an 8-byte address, depending on whether I'm using a 32-bit machine or a 64-bit machine. And then it, in one step, checks that whether the next 4 bytes or the next 8 bytes contain any null value or not, or any null character or not. And if none of the next 4 bytes contain a null character, for example, then it can just make a long jump of 4 bytes in one go. And this can give you a speed up of as high as 4x or 8x in your implementation. If there is a null character in the next 4 bytes, then you basically fall back here and you check which of those it is, and depending on which of these the next 4 bytes contains a null character, you return the corresponding value. Okay, so this is the implementation, and indeed, while I was talking, the equivalence checker was able to prove that the two programs are equivalent. So let's take a look at what the equivalence proof looks like. So we have developed a visualizer for this, and the proof basically is represented as a product graph, which basically encodes the lockstep execution of the two programs, which means that it basically correlates one step in the source program with some step in the target program or the optimized implementation. So for example, this edge here encodes the edge from start to this node encodes the correlation from the start to the head of the first loop in the source program and the start to the head of the first loop in the implementation program. Similarly, this edge here encodes the correlation between one iteration of the source program with one iteration of the first loop of the optimized implementation program. This edge here says that whenever the execution goes from the first loop to the second loop, the source program does not move at all. There's nothing that happens in the source program in this case. This thing says that one iteration of the second loop of the optimized program is equivalent to 4 iterations. There's a little overlapping here, but it says 4 here. 4 iterations of the loop in the source program. And finally, if the implementation exits, then the source program specification also does one more loop and then exit. So this kind of product graph encodes the lockstep execution, which shows the correspondences between the two programs. apart from these correspondences, this proof also encodes the relations between the variables at every step. So for example, at every node of this product graph, we kind of identify that, for example, PTR in the implementation program is equal to P in the source program, and so on. And which are also called invariants on the product graph. Now this was an example where I showed equivalence between two C programs. I'm going to next show an example where I'm going to do equivalence between one C program and one assembly program. So once again, I'm going to use this command called check equivalence, and I'm going to go to this function called, let's say, s421.c. Now similarly, I go to BLR demo and then S421 GCC EQ checker O3. Basically, it's an assembly that has been generated by GCC at O3 optimization level for the 32-bit x86 architecture. So once again, the two programs, source and optimized implementations, are shown on the left and the right, and in the middle, the equivalence checker has been set in motion. Now let's quickly examine the two programs. The source program has two loops. The first loop basically assigns some values to a variable called, to an array called ar. And the second loop basically accumulates the values of ar I into a variable called sum, and then puts it in a global variable called temp. Now on the right hand side, the assembly program basically has assembly instructions, and because it was an optimizing compiler that was used, you can see that the assembly instructions contain vector opcodes like p add d and p move dq and psrl dq. So these are all complex opcodes that are actually very difficult to understand and explain. But the point is that it's very hard for a programmer to basically manually identify that these two programs are actually equivalent or not. Now I can see that the equivalence checker is still running. Maybe it will finish very quickly. Right, so it should notify us when it finishes. And yes, indeed, it has notified us and the equivalence proof has been generated. Now, once again, I go and I say visualize proof. And once again, I have my proof as a product graph. Now, this first edge basically encodes the relation between the start to the first loop edge is basically correlated from the start to the head of the first loop in the assembly program. Now here I've shown the assembly program without all the extra comments and debug statements that were present in the .s file. And also the arguments are kind of our own internal representation of the operands as the tool sees it. This also makes for easier understanding of the proof because all the extraneous debug statements are missing here. Now this edge in the product graph encodes the fact that one iteration of the first loop of the C assembly program is equivalent to one iteration of the first loop of the C program. Now, whenever the assembly program exits the first loop and goes to the second loop, the C program also exits the first loop and goes to the second loop. When the first program makes one iteration of the second loop, which notice that is a vectorized loop, the first program makes four iterations. Once again, it says 4 here. Over here, makes four iterations of the second loop in the source program. And finally, when the assembly program exits, then the source program also makes one more iteration and exits the program. So this is what an equivalence proof looks like. Our translation validator can be used to check the correctness of a particular compilation, and it can be invoked on every compilation, especially when you're developing critical software. What is the product and research landscape otherwise for this kind of space? There's one very popular piece of software called CompilerAI in the research community, which is a standalone compiler written from scratch using a proof assistant called COQ or COQ. Here, developers manually codify proofs for every compiler pass. Recall that it's a standalone compiler which has nothing to do with existing compilers like GCC and LLVM. This is in contrast to our approach where we can use an existing compiler and validate its input and output. As a result, because CompilerAI is a standalone compiler where developers have to manually codify all these proofs, which is a very laborious and specialized job, CompilerAI only supports basic optimizations like register allocation, inlining, etc. and skips many loop and vectorization transformations like the ones that I showed you in our demo. Also, because it's a standalone compiler, it is not a full-fledged production compiler, it only supports a subset of C language, which often means that you have to change your source code a little bit to be able to compile with CompilerAI. There's another related line of work called SEL4 where, once again, there is a lot of emphasis on formal verification. ComCert was also an effort in formal verification, so that you can have higher confidence in the correctness of a compilation or a compiler. SEL4 is basically a formally verified operating system or a microkernel, to be more precise, where the lowest layer is assembly code and the highest layer is some behavioral specification codifying isolation and safety properties. The proofs of equivalence are codified manually using a proof assistant, just like it was done in ComCert. And this includes a semi-automatic equivalence checker with very limited support for optimizations to do checks between C and assembly. In contrast to SEL4's approach to equivalence checking, our equivalence checker is fully automatic and can tackle very complicated optimizations fully automatically, and that makes it applicable to general programs and not just for a particular microkernel where manual inputs were required to complete the equivalence proof. We have discovered multiple bugs over the years by testing our equivalence checker over compilers and other kind of binary translators. Here is an example of an ICC bug where there are three statements here that are two A and B are the assembly instructions that kind of simulate the operation of these assemblies of the C statements. And there's a subtle reordering that the compiler has done, which would be incorrect if r2.head alias with l.tail. So there's a very corner case situation where this kind of transformation is incorrect. And such corner case situations are very easy to miss during testing and are kind of easy for a compiler developer to make mistakes on as well. And our tool, a formal verification tool like ours, is able to catch these things, because when it tries to prove that the two are equivalent, it finds that they are not equivalent and gives you a counterexample. Similarly, we fixed a bug in the QEMU machine emulator in their PowerPC to x86 translation. Our patch was accepted, and we were even tipped Bitcoins as a thank you token for these bugs. We've also found bugs in an embedded C library called diadlibc. The exact bug was there was a missing typecast to unsigned char for *B. All these bugs that I've shown you were, and there are more, were found using CompilerAI's translation validator. And all these bugs had escaped decades of code reviews and testing by hundreds of developers. These are subtle bugs that were very hard to catch manually. Our longer term agenda is to, just like we are doing automatic proofs between assembly and C, we are interested in doing automatic proofs between C and higher layers of abstraction like functional programming languages. And we are also working on a super optimizer based on our equivalence checker. Thank you.